All right. Today I want to talk about univariate linear regression. So that's going to be the topic for today. Um, so I'm going to assume that you're like slightly familiar with linear regression, like kind of what's going on. Like you have a bunch of data points, right? And then you're trying to fit um, the line that minimizes the error, right? I'm just going to assume that that's kind of like your knowledge of what's going on, and we can just like actually get into more of like the theory of it and like what is actually a linear regression problem. So let's start with that defining a univariate function. So a univariate function is a function for which we have an input x and then we have an output y. So when we're doing a univariate linear regression, what we're dealing with is we're trying to fit a line. All right, let's just name the function that we're trying to fit. Let's just name it hy, right? And it's going to be of the form w0 plus w1x, right? We're trying to fit this into this data point that's over here, right? That's basically the goal. So in this particular case, we basically define the vector w, which is just w0 and then w1, right? But yeah, so we're trying to fit this guy in here, right? That's basically what's going on, right? So let's just be more formal. So linear regression task is basically the task of finding a WH that best fit the data. And to that, we basically find the W0 and W1 that minimize the empirical loss, right? Of course, here we'll have to decide on like what the loss is. I mean, there are different candidate here. We could go for the L1, right, which is basically it's basically gonna sum over all the data points, right? And you're just gonna take the difference between the ground truth and whatever prediction we came up with, right? Usually people don't use this one. Traditionally, people use L2, and this is just the same thing as L1, except that we basically square the answer. Yeah. So we're gonna use L2 because that's just what people do usually, right? But yeah, so once we have L2 defined, we can be more concise. So we basically want to find the vector W star such that it minimize the L2 loss, right? Yeah. And argument obviously is basically the operator that allows us to find the set of W0 and W1 that will basically minimize this guy, right? Very straightforward. So to minimize the loss, we basically are gonna try to figure out where the partial derivative of the loss function is at 0 for the different parameters, right? So we're basically going to be looking at the gradient of W, and we're basically going to try to figure out where that gradient, the gradient of L, where that gradient actually gets to the 0 vector. Let's try being a little more concise here. But yeah, that's kind of what we're trying to find in our particular case, right? It's with respect to this guy and then with respect to this other guy, right? And we want this to be this, right? In a following video, I will basically prove how you could figure out the value of W0 and W1 just starting from this equation. but for the sake of speed and for the sake of being very concise, I'm just going to tell you the answer. The answer for W1 will basically be, it's such a messy result, right? Xg, Yg, right, minus the sum, and Yg, sum, 1 and xg. It's a messy result, but I guess we don't care about that. It really allows us to find this this particular value, to have this particular a method that is a closed form method to figure out this particular value. So it doesn't really matter per se, right? But you can see that also computationally speaking, computing this value is not as straightforward as you would think, right? But once you have W1, you can easily figure out W0 because it's just 1 over n sum n of yj minus W1 xj. Right. So once you have that, you basically have the closed form. Right. We can just circle this up. Right. But yeah, this closed form obviously is only like valid for this particular case, right? We have two variables and we're trying to fit, trying to find the W0 and W1 that would better fit this line, minimizing the L2 error, right? The L2 loss. Obviously, there are case scenarios where you can't really do this, right? Like you don't really have a neat closed form like that. And in cases like that, what you want to do is you want to use, you basically want to use gradient descent, right? So gradient descent is basically, the way you think about it is there's a theorem that says that when you're in a space like this and you're trying to find the local minimum, just to be like more generalized, I guess in this particular case we were talking about non-convex problems, right? The direction of the gradient tells you where to go, basically, right? The direction of the gradient actually tells you what you need to do, and if you assume that this is the curve of this guy, then yeah, this guy basically tells you what to do, where to go, right? The direction. It means like you update. For example, it's that this was Wi, right? So you will update Wi as being Wi, right, minus the magnitude, I guess, of like the parameters that you have over here is like, it's kind of arbitrary, but let's just say a value lambda, right? A value lambda, right, times basically the loss with respect to the Wi, right? So usually that lambda is usually people use alpha, actually, and it's called learning rate. But that's basically the idea. So if you can't figure out this guy right here, because either because like, for various reasons you don't really have a closed form solution, and that would not happen in our case, right? In our case we have a closed form solution, but we're just talking like for a very generic case. What you do is you basically follow the gradient descent algorithm, which is, first step is initialize basically your W vector, right? And then you repeat until convergence. Yi is equal to Yi, right, minus lambda alpha, and then just the derivative of the loss, right? And in this particular case, Yi is just one parameter of W, right? One like dimension value of W, right? assume W vector is basically this guy, assuming I belongs to N, right? And you basically do this until it converges, right? That's basically the gradient descent. So that ends our discussion about the univariate linear regression, right? Two variables, right? You basically you basically have a closed form. You can get it using a calculus-based approach, where you basically set the derivatives to be zero, and then you basically solve for them, right? You get two equations, but you can easily solve for those. It's not too bad. Um, right, there is a more linear algebra based approach, but for this particular video, we will not get into this, right? So I'm just assuming very basic knowledge of calculus here. But that summarize it. So in the next video, I will basically look at an example of the house pricing, basically trying to predict the price of a house. But yeah, hopefully you like this.